Evening everyone and welcome back to the tutorial 11 of surface water hydrology. So in the last tutorial we did problems on frequency analysis. We were left with one type of distribution that we are going to cover in this tutorial, which is extreme value t type one distribution. And then we are going to look into the confidence interval and standard error problems related to that. And finally we are going to start the problems of tutorial 11 on the risk analysis, reliability analysis, and to estimate how we can estimate the extreme value that an hydrological event can have. So starting with the frequency analysis. So in this, we did problems on non-parametric type, which was Bull's method. So this was a graphical method. And then another type of method was parametric type method, in which there were assumptions and there were probability distributions. We read three types of distribution. One was the normal distribution, log normal distribution, and another was the log Pearson type 3. Now, in this tutorial, we will start with one of the distributions that was left at that time, which was extreme value type 1 distribution. So from the name only, this distribution was developed to analyze the extreme events that happen uh, in the hydrological cycle. So which can be, you can think of drought, you can think of floods, you can think of extreme temperatures. So this distribution is represented as if probability of x is greater than small x is 1 minus e to the power minus e to the power minus x minus beta divided by alpha. So this is the general form of the distribution where these alpha and beta are parameters called alpha is called scale parameter and beta is called location parameter. So it's the analogy can be thought of from the normal distribution where you had two parameters. One was the mean of the data and another was the variance of the or the standard deviation of the data. In a similar way, in this type of distribution, you had two parameters. One is alpha and another is beta, where alpha is your scale parameter and beta is your location parameter. So we can simplify this equation or this probability distribution by taking y as x minus beta divided by alpha. Then your equation will become 1 minus e raised power minus e raised power minus y. But the probability of exceedance from very definition earlier, also we defined the return period from this exceedance probability, that return period is actually when the probability is exceeding any value. And thus it can be written as 1 by t is equal to 1 minus e raised to minus e raised to minus. Now if you apply, if you rearrange this, so this can be written as 1 minus 1 by t. Now you apply the logarithm on the both side. So this will be log of e to the power minus e to the power minus y. This will be minus 1 by t. You can say ln, not log to the base. And this quantity will reduce. So log of m to the power n is n log. So this will be becoming minus e raised to minus y. ln of t minus 1 divided by t. Now if you take this minus on right side, you get e raised power minus y is equal to minus ln t minus 1 upon t. So this can be taken inside this minus sign. So this will become ln of t divided by t minus 1. Now you can take another log or the base e, which is ln. So your ln e raised power minus y ln of ln e divided by t minus 1 on the right side. So this will become minus y is equal to ln t divided by t minus 1. So which will imply that y is going to be equal to ln t divided by t minus 1. So this is going to be your y in terms of return period, and your standard deviation in this case is going to be 1.282 fsx alpha, and similarly then you can write s alpha as 1 sx divided by 1.282. 5 is also there. So this is one such equation. Similarly, x bar, which is the mean, its beta times 0.5772 alpha. So beta can be represented as x bar minus 0.5772 alpha. Now you can, this is here, sorry, this is alpha here. So I write it as alpha. It's not standard deviation alpha, it's actually alpha. So you can replace this alpha in this equation. The beta will become x bar minus 0.772 into Sx divided by 1.2825. So the whole equation becomes x bar minus 0.4501 of Sx. So these are your two relations. Now the y can be written also as, which is the reduced variant, which x minus the mean of y, or sorry, mean of x, which I write it as x bar. Sorry, uh, your y is x minus beta divided by alpha. So x is there, beta is from the equation this, divided by alpha, which is sx divided by 1.2825. If you simplify this, it becomes 1.2825 x minus x bar whole divided by sx plus 0.5772. Now this reduced variant yt, this can be further written as 1.2825 xt minus x bar divided by sx 0.772. So this is the basic Gumbel's equation, and in terms of if you further write it as, so xt is x bar. So if we want to calculate xt from this equation, you take the terms on the right side, so xt will come as x bar plus yt minus 0.5772 into sx divided by 1.2825. So this term is called the frequency factor. So this is the extreme value type 1 distribution, which used for frequency analysis. So the basic idea is that first you need to convert this, develop a relationship between the return period and the variant, and then from that variant you can further compute the value of xt, which is the value of that extreme event corresponding to that return period. So this is going to be your frequency factor, but this equation is, we assume that the sample size is very large in this case. Any doubts till now? So if not, then we can start the problem. So in this problem, the mean and the standard deviation of annual maximum daily rainfall at a particular state is given as 105 mm and 40 mm respectively. So what we need to determine is the annual maximum daily rainfall with 5-year return period at that state. So we have to use the Gumbel method, and we have to assume that the sample size is to be very large. So what we read earlier here, the equation, so same equation is going to get applied. The only thing is what we are known and what's known to us and what we need to calculate. So your mean is 105 mm. Your standard deviation is 45 mm. Your return period, which T is 5 years. So till now it's clear. So now the first thing that we know is that your yt is defined as minus ln of t divided by t minus 1. So we can take the value of ln here, sorry, t, which is 5 divided by 5 minus 1, which is equal to minus ln 5 divided by 5 minus 1. So if you solve this, the value comes out to be 1.5. Now, since as n is large, it's given in the problem. So we know the frequency factor is to be yt minus 0.5772, 1.2825. This is what we got from here. And now the yt we have calculated as 1.5. You subtract the value 0.5772 from it and divide it by 1.2825. You get a value of roughly 0.72. But we know, let's say xt is given as x bar plus. So this is a standard equation that we use in the case of parametric method in the frequency analysis. Now your x bar that's also given in the problem is 105 plus your frequency factor is 1.5 and your variance is, or the standard deviation is given as 40. So if you solve, xt will come out to be 105 plus, I'm sorry, the frequency factor is 0.72. So this needs to be calculated. So this value comes roughly around 137.4 mm. So this is your annual maximum daily rainfall that's going to be associated with the 5-year return period using the Gumbel's method. Any doubts? So if not, then we can start with the confidence interval and standard error in frequency estimates. So now in the previous problems, what we try to do is we were trying to calculate that frequency estimate, whether it was a return period or whether it is a discharge associated with the return period. But once you are making these calculations, there will be an error that's going to be associated with that estimate, or there will be some probability or some confidence that we know exactly that this value is the exact value. So then in case of confidence interval, so from the name only, so we try to find a probability that x is going to lie between two limits rather than there is an exact value of that, uh, rather to directly pinpoint that value from the probability distribution. So let's say you have your probability distribution, and let's say this is your lower limit, this is your upper limit. So let's say this xt belongs in this area, so xt belongs to this, so it can lie between xn and xu. So this area I can represent it as by alpha, this by alpha, and this by beta. So I can write it as xl and xu are confidence limits, upper and lower respectively. This one is going to be lower and this one is going to be upper. And the probability that xt lies between xl and xu is equal to beta. That's the area under this curve. The vertical bars in. Since total area under this curve, this probability curve is to be going to be 1, which 2 alpha plus beta is to be had value 1. So alpha is going to be 1 minus beta divided by 2. Now if we talk that, let's say there is 95% confidence, that means your beta is 0.95 and your alpha will become equal to 0.025. Now, one of the important thing is to estimate this upper limit and lower limit. So upper limit is estimated as mean plus kt comma alpha. So the frequency factor is going to change. Mean and variance will remain same for the data set. So this kt alpha of u, kt alpha of l. So these are estimated. So using the t distribution, in case your x follows the normal distribution. However, in case of Pearson, let's say your x follows Pearson 3-type distribution, then this xt alpha of u is estimated at kt plus under root of kt square minus ab divided by a. Kt alpha of l is defined as kt minus under root of kt square minus ab divided by a, where a is written as 1 minus square of first square divided by 2 into n minus 1, and p is kt square minus z alpha square upon capital N. So z alpha is the standard normal variant. We know how to calculate it. Xt minus x bar upon mu with exceedance alpha, and n is the sample size. Any doubts till now? So if not, then we can do a problem on this. So let's say you have to assume that you are assuming that annual maximum discharge data follows a log Pearson 3 distribution. So it's the same data set that we used earlier, the previous problems. That's why I have not put it here, the table. And we need to determine 95% and 99% confidence interval for 100-year maximum annual flood. So if you remember, the mean we calculated at that time was 3.427. Your variance was 0.208 and your coefficient of variation was 0.021. And if you remember, K lower limit for this return period was 3.326. Upper limit was around 2.4. This was corresponding to when CS was 0 and this was corresponding to when CS was 0. Since we need the K corresponding to CS 0.021, we use the concept of linear interpolation. So it will be K100. So this value will be equal to K100 equal to 2.326 plus 2.4 minus. So this becomes around 2.341. Now we are given that we need to determine confidence interval for 95% probability, 95%. So for 95%, your beta becomes 0.95. As I said, alpha becomes beta 1 minus beta divided by 2, which is equal to 0.025. And Z alpha comes around to be 1.96 corresponding to this alpha value. This can be taken from the table, standard normal variance table. So what we need to do is first is to calculate the value of A. One. N, your N is minus 1. So this is going to be 40 minus 1. N is 40 in this case. So the value comes equal to be 0.951. And similarly, your B is KT square. So this is 2.341 square. This comes out to be 5.384. KT alpha of U is KT plus under root of KT square minus AB divided by A. This becomes to be mu. This is 3.0926. And similarly, if you estimate lower value of KT, value comes out to be 1.306. So the 95, so what we need to calculate is the 95% confidence limits, which is Y U, I can say upper limit one, Y bar plus KT, gamma alpha of U, SY. So you know the Y bar, you know the KT which you have calculated 3.09, you know the standard deviation. This comes 4.0702. We know log of 10 of x u is yu, implies that xu is 10 to the power yu, 10 to the power 4.702. The value comes out to be 11754.3 cubic meter. And similarly, you can do for YL, which will be y bar plus kt comma alpha of L sy. This will be 47 plus 63. This value comes out to be 3.8077. And if you calculate XL, then that will be 10 to the power YL, which is 10 to the power 3.807. This comes out to be 6422.44 cubic meter. So these are the upper and lower limits of the confidence interval of 95% corresponding to the data we have in this problem. So any doubts on these two problems? So this makes the conclusion of the frequency analysis topic, and we are now shifting to the tutorial 11. So in the tutorial 11, I will start with the concept of extreme estimated, sorry, limited. So this is the maximum value I can say, minimum also, that an hydrological extreme event can have. So now let's say, for example, you have flood. So minimum value is that, or the discharge I can say, not flood. So the minimum value can go to 0 in a stream, but maximum will be some finite quantity. So overall, in the hydrology, since every quantity is finite, so this estimated limiting value be have significant or a particular quantity, not in any infinite values. Now for the designing purpose, the important thing is that we should have a good knowledge of these limited values for which we can design. And also from the frequency analysis, we estimate the turn period and how much confident you are about that turn period. And once these things are known, ultimately the design and the structure that needs to be constructed. So we are mostly focused on the safety purpose and on the cost purpose also. And it should serve the the benefits that we need from the structure that we are going to build. So for any hydrological event, to estimate this design or the scale or these limiting values, there are different approaches. So I can say it is magnitude of hydrological event to be considered for design. We have three approaches. One is empirical one. Second is the risk analysis. And the third is the hydroeconomic. So this hydroeconomic part will include the cost. The risk and approach does not include the cost purpose. So we can start with the empirical approach. So these all has to be, so they determine the design value. So the empirical approach is more like a rule of thumb that involves arbitrary factor of safety. And from that factor of safety, you compute the design level. So one of ways through which we approach in this empirical formulation is that we calculate the probability. So one is that, let's say you have an event, hydroclimatic extreme event that exceeds uh, so probability that most extreme events of an past 10 year will be equal or exceeds once during the next 10 years. So in the future, let's say 10 to 15 years. So what's the probability that the some hydrological extreme is going to exceed that has occurred in the last, I think, 20, 30 years. So this is given by n upon n plus n. So if I write it, this is probability that most extreme events of the past now let's say that extreme event has some duration. So it can have a duration, it can persist for 1 year, 2 year, 3 year, or few days. Now let's say that event lasts for m years. So then this equation becomes, if you simplify this, this is the equation. Now we can start with the problem on this. Welcome back. We can start with the problem. So in this problem, we have to analyze the soil moisture record. Soil moisture records are analyzed for the time period of 1971 to 2020. So it's observed that critical agriculture droughts last for 3.5 years. So the events here are droughts. So droughts are when the soil moisture or water level, different water levels, whether it be stream flow or soil moisture, falls below some threshold. So you can think of that there is no water availability over that period of time. So there is a drought event of 3.5 years. We need to evaluate the probability of occurrence of more severe drought in the next 25 years. So more severe here means that a drought that lasts more than 3.5 years. This is a similar case what we read earlier, that probability of occurrence is n minus m plus 1 divided by n plus small n minus 2m plus 2. Now the important thing to note here is that your capital N is the time period in which you are analyzing. So this will cover 50 years. Similarly, your M will be 3.5 years, which is the duration of event. And your small n is in what number of years you are expected to have more severe drought, which is 25 years. If you use above equation, it's 50, 3.5, comma 25. Put the values. So this will be roughly 22.5 divided by 25 minus 7 plus 2, which is 17. This will come out to be 0.7. So the probability of occurrence of more severe drought in next 25 years will be 32%. So any doubts on this? If not, then we can start with the second method, which is the risk analysis. So in this risk analysis, we are first going to understand what's risk. So it's defined as the probability of occurrence of an event which occurs at least once over a period of n years. So this is what we have earlier done also. Probability of occurrence of an event at least once over a period of n successive years. And this R is mathematical term. It will be, if it's a probability of occurrence of an event, then R can be also written as 1 minus probability of non-occurrence of occurrence of events. And this is 1 minus 1 minus p whole raised power n, because we are focused around n years. So this is 1 minus probability of success, which is 1 by t whole raised power n. And this is the risk. So for any extreme or hydrological event, the risk that is associated with it is given by R is 1 minus t whole is power n. Any doubts on this? If not, then we can start with the problem. The problem is that you are told to, so there is a flood embankment built along the side of a river that has an expected life of 25 years. So for an acceptable risk of 10% against the design flood, so we need to first estimate the return period. And once you estimate the return period, then if the above return period is adopted and the life of the structure is to be revised to 50 years. So what is the possibility and what's the possibility of new risk? So in the case first, your acceptable risk is 10%. So your risk is 0.1 if I write by 100, since this is in percentage. But we know the risk is 1 minus 1 minus t whole raised power n. And If you simplify this, so value of n is given in the first part, it's to be 25 years. And if you solve this, you get n value of around 237 years, which is roughly you can take it as 250 years. I think this will be 57. So once you estimate the return period in the second part, it said that now they're using the same return period, but the life of structure has to be improved to 50 years, which was earlier, I think, 25 years. Now, what's the risk that is going to be there if we implement this? So, you know, the risk is 1 minus 1 minus 1 by t whole raised power n. So, return period remains same, which is 250. And your n now changes, n goes to 50 now. So the risk becomes 1 divided 1 minus 1 minus 4 is per 1 by 20, 250 4 is per 50. So if you solve this, this value comes out to be 0.18. So the risk is roughly now 18%, which earlier was only 10%. So as you increase the life of an structure, so the risk associated with it will increase for the same return period. So you are not changing the return period, you are just only increasing the life of the structure, or you are designing for a longer time period. Is this clear? So next thing that we have is reliability. So reliability. So it's opposed to the risk that we read. So it's actually defined as the probability that no extreme event, that's x greater than xt, will occur during the lifetime of an uh, structure that we are designing. So there will be no occurrence of that extreme event during that period. And this is our ELI. It's defined as probability of non-occurrence, which is 1 minus p 4 is for n. If you put the value of p, then it's 1 minus 1 by t 4 is for n. And the important thing after this is the factor of safety. So factor of safety is defined here as C upon L, where C is going to be your actual value that you are adopting for design. And the second thing is the hydrological design value. Now, we can do a problem on this. You are being asked that there is a barrage which is being constructed for 50-year design life across a river with 10% risk. Now, the analysis of long-term annual peak flow data in the river gauge gives a mean, and we know the standard deviation. So we need to estimate the design flood of the barrage, assuming that peak flows follow the Gumbel extreme value distribution that we read in the starting of the tutorial. So if the factor of safety is 1.5, so this is the first part, and now in the second one, if the factor of safety is 1.5, 5 and what will be the design flow. So if you remember, so I will just first write what is given to us. So you are known to have a mean of 1500 and a standard deviation of 500 cubic meter. Now your risk is 0.1 and this risk I can write it as 1 minus 1 by t whole raised power n. Now your life, construction life is 50 years. So this implies that 0.9 is 1 minus 1 by t whole raised power 50. If you solve, t comes out to be around 500 years. So this is the return period that was we calculated for the risk of 10% on having a life of 50 years. Now for Gumbel distribution, if you remember, your yt was minus ln of t divided by t minus 1. Your t is here 500 years. If you put the value, you solve this comes out to be 6.2136. So the reduced variant you have is 6.2136. Now you know the frequency factor is calculated as yt minus 0.5772 divided by 1.2825. Now this yt was 6.2136. If you calculate this, the value comes out to be 4.395. So xt is x bar plus kt of sx. Now your x bar is 1500 plus your kt, I can put the value here, 4.395 and your variance is 500. This value comes around to be 3697 cubic meter. Now in the second part, you are told to consider a factor of safety to be 1.5. So the design load will be 1.5 times the value that you computed here. And this will become 1.5 times the xt is 3697.5. If you calculate this, the value comes out to be 5550 cubic meter. So any doubts till now? So if not, then I'll stop here. We can meet in the next tutorial, which is the last tutorial of this course. Thank you.